So we spent a week studying kinematics, which describes motion, and that's the first step towards studying the laws of physics in mechanics. Now, physicists like their laws to be very general, and that means that they like to have one law that describes a bunch of different phenomena, okay? But often in the real world that doesn't quite work out, okay? In the real world we always have to make approximations to explain what's happening. And also when you're just learning physics, that usually doesn't work. When you're just learning physics, we describe such simple situations that usually we have to make approximations just to be able to do the math. It's sort of the early level. So I want to show you a couple of examples of where what we've been doing actually isn't quite so general. Okay? So let's see. So one example is in all the kinematics we've done, we've assumed the measurements were in an inertial reference frame. What? An inertial reference frame. Sort of a long, complicated name for something that is simply, my simple definition, is coordinate systems that are moving with respect to each other at some velocity but are not accelerating. So inertial reference frames can move. So you say we have one here. Here is a reference frame which you can think of just as a coordinate system. It's a system to measure the position of something, and we'll call it X and Y of, let's say, of Hertzian amphitheater. That's we are, HZ for Hertzian amphitheater, and it just sits there. I could imagine my own inertial reference frame, and I have my own coordinate system, and maybe I'm moving to the left, right? So that would be one, if we wanted to draw it sort of schematically, is here is X JH, that's me, Y JH, and this reference frame, or coordinate system, is moving with some velocity the whole time, okay? The reason this is important is when we derive kinematics, all these equations of motion, they work in both reference frames, okay? The equations of motion we've described will work in this reference frame, they'll work in this reference frame, but you'll get different values, okay? So if I have Hal here and I roll him like that, he has some velocity. As we watch as a function of time, we get different positions. That's what velocity is, the rate of change of position with time. But if I'm in a reference frame where I'm also moving, if I look at it, I just measure a constant position. I measure zero velocity. And I don't even have to be going the same speed. It might be that Hal's going that fast and I'm going less fast, but at a constant velocity. Then I would measure a velocity that would be slower than what you measure in the Hertzian amphitheater frame. So different reference frames isn't usually something you think of because there's a very natural one. The natural one is the frame of the building, right? What we think of as the stationary frame that you're standing in. And you think that's the natural one, and it is. And often in a problem they'll say use the lab reference frame. The lab means the building. But for some problems it's useful to think about different frames when we get into momentum and collisions, things like that. So if you're learning about kinematics and you keep seeing these references to inertial reference frames, that's what they're talking about. And also, all the kinematics work unless you start having them accelerate. And then lots of things become complicated if you get into an accelerating reference frame, and we won't even deal with that for a while. Right? So for now, let's just think about inertial reference frames. Another thing that I can show you where the laws don't quite work or where you might not be as simple as you think is with this setup right here. So we talked about how when something falls near the surface of the Earth, it falls at 9.8 meters per second squared. Right? So here we have this little steel ball. It certainly falls at 9.8 meters per second squared. And to put it here, and it's on this hinged arm, And on the arm, a little farther down, is a little bucket. Right? And you can see the lip of the bucket is above the ball. And the bucket is going to fall, and because of the curve, it's going to end up under the ball, but it actually has farther to go. And it has farther to go, and it can't fall faster. There's no way the ball's going to end up in the bucket, right? So if there's anything, it's going to be too late, and it's going to bounce off. Right? So let's pull the little latch here and see what happens, and there you go. The ball went straight into the bucket. Now, how could that possibly be? We just learned that everything falls at 9.8 meters per second squared or slower if it's going down a plane. And this is a case where we have little technical things in our definitions, and we have broken the rules here. The rule was something falls at 9.8 meters per second squared if it's free fall. Well, this is not free fall. The ball undergoes free fall, but this is a constrained motion. This is a rotation. Okay? So you got to be careful sometimes when you apply the laws that you're learning. They don't always apply to every possible situation. You got to watch for the details. Usually in a physics problem, if a word is added, like free in front of fall, it's put there for a reason. It's not just, oh, we felt like saying free fall this time. It means it only applies under free fall, not under constrained motion. So those are just some things to watch out for. Everything you're learning isn't perfectly general, but when we teach you how to do problems, we're trying to teach you when to use this equation, when to use that equation, when they're appropriate, when they're not appropriate.